Alright, gang, here we go. This is for Chem 2 Unit 9, talking about kinetics. Alright? Specifically, we're going to be talking about factors that affect reaction rate that we haven't talked about yet. And most excitingly here, we're talking about activation energy. First couple of things here will be pretty obvious, and then we're going to learn some new exciting stuff about activation energy. Okay, temperature and rate. Generally, as temperature increases, rate increases. That's pretty surprising. We'll do this in class. We'll take like a glow stick, put it in hot water, and you'll notice it gets brighter. And then cold water, it gets dimmer, and that's because the reaction is slowing down or speeding up depending on the temperature. Remember, your rate constant, that lowercase k value, is temperature dependent. As your temperature increases, the rate constant increases. All right, and it's kind of interesting. It follows this kind of logarithmic thing here that as your rate constant doubles, you can predict it's like a 10-degree rise, Celsius degree rise. So like every 10 degrees of Celsius, your rate constant pretty much doubles, which is pretty fascinating. All right. Uh, Now, your frequency of your collisions, now we talked about this when we first talked about reaction rate, is this model is really based on the kinetic molecular theory. We talked about this at length when we talked about gases. All right, so essentially we're saying that in order to react, these molecules have to run into each other. If there are more collisions, there are more reactions, okay? And it's all about whether or not you have effective collisions. And these effective collisions result in a chemical reaction. You break old bonds and you form new bonds. And then, so these molecules can really only react when they hit each other. Okay, and so the first thing that affects them is that they have to have the right orientation. All right, they hit each other, and if they don't hit each other just right, okay, then they just bounce off each other, and you don't actually have the chemical reactions. If you align them properly, you actually get these chemical reactions. All right, so for example, here's chlorine, or no, this is, shoot, I don't even know what that is. It's some other thing. Okay, and so yeah, anyway, so this chlorine atom is bouncing into this guy, and if it hits another chlorine atom, then you get this reaction of this Cl2 being able to bounce off in this blue and red molecule. I'm sure after I'm done recording, I'll be like, oh, duh, that's what this is, but for the life of me right now, I cannot remember what this is. Yep, nothing. Okay, but if it bounces off instead of hitting the green one, it hits this red one instead. They're not in the correct orientation, therefore you can't have a reaction. No effective collision. And there you go. So you have to have the right orientation. All right. Another thing you need is that you have to have enough energy for the reaction to take place. And this is called the activation energy. All right. And you probably learned about this in biology or Chem 1. Okay. And it's the minimum energy needed for the reaction to take place. All right. You could almost think of it as like a golfer trying to hit a ball. If you've ever been mini golfing, you know, you just need to hit it just hard enough to get over the hill so it'll roll off and land in the ball. Right. And so in chemistry, we can almost think of it like that too. Like in order to get your reaction to take place and form your products, you have to give it just enough energy to get over the top of the hill. Okay, and so that's so it's essentially like that idea here. Okay, and when this occurs, we form this thing called a transition state. It's also known as an activated complex, and you'll probably hear me say both of them interchangeably. All right. And so what happens is you have your two reactants and they hit each other, okay, and they gain energy, and then they reach this maximum energy state. And this maximum energy state is known as the transition state or the activated complex. All right, and so this is the most unstable organization of your reaction, or of the entire thing. Okay, and so the energy needed to form the transition state is known as the activation energy. All right, so this plot here, okay, is your reaction progress plot, your energy diagram, and you can use this to help you figure out what's going on in this reaction. All right, so in the left-hand side we have energy, potential energy, and in the y-axis, in the x-axis we have reaction progress. Okay, right here are your reactants. All right, these are your reactants and these are your products. Okay, now, so this guy here, we've looked at this reaction before. Okay, essentially all that's happening between, if you just look at the reactants and the products, essentially what's happening is your N and your C are flipping places. Your N is in the middle right here, and your products, your C is in the middle. And you know that nitrogen is more electronegative than carbon, so it makes sense that carbon should be the one in the middle, and you can see that it's actually at a lower energy state. Okay, now, in order for this reaction to take place, this is the activation energy required. You have to put in this much energy, okay? And it kind of shows you during these diagrams what's going on here. So originally your reactant is planar, right? It's just sticking out here in this line. And then as it gains energy, it gains enough energy to break this steric interference and be able to start to bend away from the plane. Okay, and it starts to bend over until eventually you reach this most unstable version of itself, all right, where your carbon, this triple bond is completely perpendicular to this carbon bond. All right, and this would happen just instantaneously. Okay, notice that we use this dashed line to show this, this new, it shows both the bond being broken and the bond being formed at the same time right here. Okay, and then as it falls back down the other side, notice that the carbon is now in the middle, and so and then the nitrogen is swinging into place to be right here. And you can see, so if you just kind of plot what happened to this carbon, the carbon went this way, and then it's going to keep going this way, and the nitrogen is going to keep going. It's going to start swinging out this way, and you form this, and you can kind of see what's going on here. Okay. So at the highest state, that's your transition state, or your activated complex. All right, and we can also see whether or not our reaction is exothermic or endothermic, and all we have to do is look at our delta E. If our reaction released energy, if our delta E was positive, okay, then that means we would have an exothermic reaction. So this reaction here is going from this reactant to this product, and we can see that this change in energy right here, well, we'd have energy left over. Right, we had this much, and then now that we've ended here, we've got this much energy left over, so this would be an exothermic reaction. If the products were above this, it would be an endothermic reaction. Okay, and so your rate constant, okay, depends on the magnitude of the EA, of the activation energy. The bigger your activation energy, the smaller your K value is going to be. Okay. All right, and this really happens because of this idea here. Right down here, and we've looked at graphs like this before. Here's your fraction of your molecules that have this amount of energy, kinetic energies in the right-hand side. Now what we're saying is this dashed line here is the minimum energy needed for the reaction, or the activation energy. Okay, anything past this line has enough energy to break those old bonds in order to form the new bonds. If you're at a lower temperature, there's a lower percentage of your total molecules that have enough energy to get the job done. At a higher temperature, our molecules are, shift ever so slightly to the right. Okay, so now we have more molecules, a larger fraction of them are available to have enough energy to make the reaction occur. Okay, so there's a larger fraction of these molecules that can react because they're at a higher energy, because they're at a higher temperature. Okay, and so because of that, and so we can contribute these two things. We already talked about how your kinetic, or your increase of temperature increases your K value. So increasing your K value would also correlate with having a lower activation energy. All right. So this relationship between the activation and energy this relationship was correlated mathematically, sure, by this guy named Arrhenius or something like that. Okay, Arrhenius. All right, and he formulated it as this: is the K value is equal to your A, okay, times e to the negative EA over RT. Okay, and so you can use this to, if you have your K value, or if you have your activation energy, you can take this guy to figure out your K value. All right, and then if your activation energy, and then you could also graph this relationship by simply, if we take the natural log of both sides, we'd get something that looks like this. And from your experience with reaction orders, you should say, hey, this looks a lot like y equals mx plus b. All right, plus b. Okay, our slope. So our y value is this. Okay, and then our b value would be this. This would be our slope, our intercept. Okay, and then our m value, well, that's our slope. So this is always just a number. Well, that number would be our negative EA over r. That would be our slope, and then our x value would be 1 over temperature. Okay, and then for this last one, they took out all this and they rearranged it again. So this is an important formula here, the Arrhenius equation. All right, so if we took these guys, what we just said, our y equals mx plus b formula, and we plotted it, natural log of k and the inverse of temperature, and we found the slope of that line, we would know that that's equal to the relationship of the activation energy over the temperature, or over the R value. Okay. And so this R value, okay, one thing to keep note is this R value has to be, because it's an energy, has to be the 8.31 for joules per mole, okay, value. All right. So we're looking at these activation energies and speeds of reaction here, and it says rank the forward rate constants from smallest to largest, assuming all three reactions have nearly the same value for the frequency factor. Oh yeah, that was that A value is that frequency factor. Each reaction has kind of their own frequency factor. It's just a way of making sure that it's no longer, without that value, that equation would be a proportionality instead of an actual relationship equality. All right. So anyway, so we're equating these guys. So remember, the bigger the activation energy, the lower the K value. All right, and we're ranking these K values from largest to smallest to largest. So really, we just have to figure out the activation energies. All right. Well, the activation energy for this one would be 15 kilojoules per mole. All right, and the activation energy for this one would be 25, and the activation energy for this one would be 20. Notice that don't get thrown off here by this 5 kilojoules that's floating out here. This from this to this would be 15, and you might be thinking, oh, that's equal to this one, but it doesn't really matter because that's our product. We don't care about this change. The activation energy is only from here to here. That's your activation energy, and that's 20. So from smallest K to largest, well, that would be 2 has the largest activation energy, so it's got the smallest K value, and then 3, and then 1. So 2, 3, 1 should be the answer. Yep, and that's what they got. 2, 3, 1. All right. All right. Let's see. Which of the following changes always leads to an increase in the rate constant for reaction? Decreasing the temperature, decreasing the activation energy, making the value of change in E more negative. Always leads to an increase. Well, number 2 definitely does. Okay, making the value, if we, let's see, if we lower the activation energy by adding like a catalyst or something like that, that would increase the rate constant. Okay, that's always true. So 2, and then number 1, decreasing the temperature, no, that can't be right. So it's got to be D. Or no, never mind. D, or let's see, making the value of delta, that doesn't make it change anything to do with the rate constant. Okay, so 3's out, so it's got to be A, just be number 2. Okay. All right. Ooh, this one's interesting. So it says rank the rate constants of the reverse reactions from slowest to fastest. So we can look at these guys and do them backwards now. Okay, from slowest to fastest. So now we're looking at from this, up here, okay, and then here to here, and then here to here. So the fastest will be number 3 because its activation energy is only 15. Okay, this guy's activation energy is like 25 plus 15, so this would be 40, and this one would be 25. Okay, so slowest to fastest would be 2, 1, 3. Okay. Okay. All right. Last little bit here says determining the activation energy. So this is kind of an interesting question here. All right. And we're just going to follow along with their work. First, we're going to talk about, well, what would we do to solve it, and then follow along as they do the work. All right. It says the table at right shows the rate constants for the arrangement of methyl isonitrile at various temperatures. Okay. And they tell us to do two things. From these data, calculate the activation energy for the reaction, and B, it says what is the value of the rate constant at 430 Kelvin. Okay, so in order to get the activation energy, we know that the slope, if we can graph the natural log of Kelvin, or of the K value, sorry, and the inverse temperature, we know that the slope, and we graph this guy, the slope of this would be equal to negative EA over R. So if we solve for that, then we can get that. All right, so that's not too bad. It's be a lot of work. We have to, take the natural log and inverse of all those temperatures, make sure these are in Kelvin, okay, and then we graph it. We should be good, and we can multiply it by the R value, and we get the activation energy, okay. And then it says what is the, or negative R value, excuse me, and then B says what is the value of the rate constant at 430 Kelvin. Well, in order to solve for that, all we have to do is use this formula. Oops, oh crap, I held it down way too long, it got lost. We got to use this guy here. because we'll have these two temperature values. We can use any of the temperature values we have, and after we do step A, we'll have the activation energy, and then we can just simply solve for one of these K values, okay, depending on where we plug it in and all that stuff, okay. So let's see what they do, okay. So EA from the slope, natural log K versus inverse temperature. All right, good. So they got this graph here, or this table. So they converted into Kelvin, just like I said. They took the inverse and the natural log of the rate constant here. Then they graphed it, and they found the slope of this line, and we know the slope is equal to negative EA over R. Okay, now they asked specifically for the negative EA, so EA, the activation energy, would be equal to negative R times the slope. Okay, so they're going to do that next, I'll bet. All right. Oh, there it is. So they found the slope. That's what the slope is equal to. Okay, and there it is. So the EA is equal to negative slope R. So they took that times 8.314 and they converted into kilojoules. All right, and there you go. So there's your activation energy. Okay, 160 kilojoules per mole. And then for part B, all right, for part B, they want to determine the rate constant. So there's your T1 value. All right, so they're using their 430. The one they're trying to find is their T1. We're trying to find K1. That's your unknown. And you're going to use that same equation we just looked at. There's your activation energy. And then really they just chose this rate constant, okay, and this temperature. And you could use any of them, okay. And then from there, it's just simple algebra to take that guy and plug it in. All right, and so they took the natural log of K1, and that's equal to all that. And so the right-hand side is equal to negative 3.18. And then in order to get rid of the natural log, you take the E of both sides and then you multiply it by this. Okay, so the K value at 30 Kelvin would be 1 times 10 to the minus 6th. Okay, and then note that the units of K would be the same, right, because it's still the same order of reaction, but because we're at a lower temperature than we were at 462.9 Kelvin, we have a much lower K value. It was 2.52 times 10 to the minus 5th, and now it's 1.0 times 10 to the minus 6th. And that's it for this stuff. So, some more stuff to put in your hat as far as kinetics, things you can do with kinetics. A new formula that can be kind of tricky. That Arrhenius equation can be kind of rough, but just do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.